All right, for all you AI builders out there, you know the deal. Models can be absolute beasts. They're incredibly powerful, but man, they are huge and slow. So today, we're going to dive into a total game changer for taming them, a technique called quantization. This is the secret sauce that makes running powerful AI on your phone or laptop not just a cool idea, but actually practical.
And this right here, this is the core promise. This is the one sentence that gets everyone so excited about quantization. It's all about efficiency. It's about taking these amazing but massive models and making them usable, deployable, accessible to everyone. So how does it pull off this magic trick?
Well, first, let's set the stage. Let's talk about the problem we're all trying to solve. You've probably been there. You've trained or downloaded a state-of-the-art model, you're ready to build something incredible, and then you hit a wall. A very big, very slow wall.
Yeah, this list should look pretty familiar, right? These models demand a crazy amount of memory, they need powerful, often expensive hardware to even run, and the time it takes to get just one prediction, what we call inference speed, can be painfully slow. All of this creates this massive barrier to the dream, you know? The dream of running things like real-time translation or cool creative tools right on our own laptops and phones.
So you're staring at this big model problem. What's the solution? Well, it's this really elegant and powerful concept called quantization. And what it does is it directly attacks that size and speed problem right at its very core.
At its heart, quantization is really all about simplification. See, an AI model is basically just a giant collection of numbers. We call them weights. They're the parameters the model learned when it was being trained. Quantization just reduces the precision of these numbers. You can think of it like rounding them off, but in a very smart, structured way, like going from a super detailed 16-bit number to a much simpler 8-bit or even a 4-bit one.
And this, right here, shows you exactly what's happening. On the left, you've got this high-precision number with all those decimal places. And on the right, you have the quantized version. It's still representing the same basic value, but it's using way less information to do it. It's simpler, and that simplicity is exactly where all the savings in memory and speed come from.
This is honestly the perfect analogy. Imagine a beautiful, high-resolution photo with millions and millions of colors. That's your original high-precision model. Quantization is like telling the computer, okay, redraw that same picture, but you can only use a few thousand colors, or maybe just a few hundred. The main picture is still there, right? You can totally tell what it is, but the file size is just drastically smaller.
Okay, so we get it. It's about making the numbers simpler. But how does that simple idea actually translate into real-world speed boosts? Let's pop the hood and take a quick look.
So the core idea, as we said, is using fewer bits. Now to put that in perspective, a 16-bit number can represent over 65,000 different values. An 8-bit number, only 256. That is a massive reduction. And the best part is, the most common way to do this is something called post-training quantization. You just take a model that's already been trained and convert its weights. No need for expensive retraining. And if you're looking to get your hands dirty, you'll often find these models packed into a really popular format called GGUF, which is specifically designed to make running these efficient models on everyday computers super easy.
But, and you knew there was a but coming, right? Like with most things in engineering, this isn't exactly free. There's a fundamental trade-off that every single builder needs to understand before they jump into quantizing a model.
This table just lays it out perfectly. As you move down the list, from 16-bit to 8-bit and then down to 4-bit, your memory usage just plummets and your speed goes way up. But take a look at that last column, potential accuracy loss. By simplifying all those numbers, you might lose a little bit of the model's nuance. For 8-bit, that loss is often tiny, almost unnoticeable. But when you get down to 4-bit, it can start to become more significant.
So, here's the crucial takeaway. There is no single best option. It all depends on your project. If you're building a fun, creative chatbot, a little bit of error might be totally fine. It might even make things more interesting. But if you're building, say, a medical diagnostic tool, then accuracy is absolutely everything. You have to match the level of quantization to what your project actually needs.
Okay, so we get the what, the why, and the big trade-off. So how do you actually put this into practice? Let's just walk through a really simple mental model for how you can apply this to your own work. It really just boils down to these 4 steps. First, you pick the awesome, high-quality base model you want to work with. Second, you decide on your target bit width. Are you going for 8-bit, 4-bit? That's based on the speed versus quality trade-off we just talked about. Third, you use a tool or find a pre-converted model in a format like GGUF. And finally, and this is without a doubt the most important step, you test it. You have to make sure the performance and the quality are good enough for your specific use case. And that's really it.
This whole straightforward process is the key that unlocks the door. It's how we take these massive, cloud-based AI models and we bring them home to run on the devices that we use every single day.
This really just changes the entire landscape of what's possible. The old barriers are coming down, and the power to create amazing things is being put directly into your hands. So the final question really isn't about the technology anymore. It's about your imagination. Now that these incredibly powerful models can run almost anywhere, what are you going to build?